You can hear me all? Okay, great. So I'm going to talk today about another networking virtualization project, although this is for a slightly different purpose. Instead of creating infrastructure for various tenants, this is creating infrastructure on your laptop for a single tenant who might be a network application or operating system developer. And so I'm going to talk about a few things. One is the motivation for Mininet, which is making a development platform for software-defined networking. Talk a little bit about what it does, which is create processes and network namespaces. Give a brief demo of Mininet and talk a little bit about its API, and then talk about experiences we've had using Open vSwitch for software switching in Mininet. So the motivation really for Mininet was back when I was working on OpenFlow, and it really became clear that for OpenFlow and software-defined networking to succeed, we really needed a development platform that people could run on their laptops that wouldn't require a big stack of hardware. And really you wanted to be able to, the goal was to be able to run the same network OS and application on your laptop and then move it seamlessly to hardware, much the same way that if you want to develop a mobile app like on your iPhone, sure you can run it on the phone, but it's really useful to have a phone emulator on your laptop because you may not have all those devices. For Android, it's much even worse because of fragmentation. And in any case, with the phone, it's easy to get a piece of hardware, but with the network, you have all these different boxes, and so how do you do it? And so to start with, I'm going to talk about how you'd emulate a very simple legacy network. Forget SDN for the moment. The simplest possible network we could imagine. 2 hosts, a single switch, and a sort of client and server application. And what we're going to do is we're going to use the a la carte network virtualization features and actually just operating system level virtualization features in Linux, in particular network namespaces, which will allow you to attach a particular different set of network interfaces and IP addresses to different ports. And so we create one network namespace with one virtual Ethernet interface that has Firefox in it and another with HTTPD in it. We can assign separate IP addresses to each interface, connect them via virtual Ethernet pairs to a software switch, which is probably going to be Open vSwitch. It's the most common and popular software switch that Mininet uses. And you could easily set this up by typing in a bunch of Linux commands. In fact, here are all the commands to create some namespaces, create a switch, create links, move the ports around, start up OVS, connect the switch ports, set up a controller. So now we can make actually an SDN network that has an OpenFlow switch connected to a controller, and then configure your network and maybe run some tests on it. In this case, just ping it to make sure it works. So this is nice, but you might ask yourself, wouldn't it be great if we had a simple command line tool or API to do this for us automatically? And so maybe something that allowed us to easily create topologies of varying sizes, maybe parameterized, hundreds of nodes and run various tests on them. And what if, to add a bit of icing on the cake, it was already included in Debian or Ubuntu that you may already have in a VM or on your laptop or on your server? Well, that's exactly what we did. It's called Mininet. Here's our webpage, mininet.org. So if you have Ubuntu or Debian, you can just apt-get install it. You can check out our website. And I'm going to give a short demo of Mininet just to show you how it works. So hopefully I'll remember these things. If I don't, we can go back. So let's see, can you see? Oh, no, you can't. That's interesting. It's off the top of the screen. Oh, this is interesting. Okay, I may have to move this down a bit. So can you see it clearly with the green, or should I reverse it? Well, let's see. Is this okay? Can you see that okay? Okay, great. So just to start up Mininet, just mn, and just typing mn creates the simplest possible network that we've described here. 2 hosts, 2 switches, and a controller. In this case, it's a default controller that just implements a learning switch. And we have a Mininet command line where we can talk to our hosts, one command line to rule them all. h1 if config shows that h1 has address 10.1, h2 if config. h2 has 10.2, and we can send commands to h1, tell it to ping h2, and find that our network does actually work, which is great. And of course, that's a very simple network. We can make a more complicated network if we want to. We have these idea of parameterized topologies. So I can make a tree network, depth 3 and fan out 3, and actually do the right command, topo. It's a topology. Oh, did I need to do this? 3, 3. It's the wonderful thing about live demos. And in this case, it'll create a network consisting of 27 hosts. Once again, they're processes and namespaces. 13 Open vSwitch switches and linked all together. And hopefully we can check connectivity using this ping all command, which will run pings between all the pairs. And of course, since this is an SDN network, it's doing something kind of interesting. It's doing reactive forwarding, implementing a learning switch, and actually every flow has to talk to the controller. And if we do it the second time, all the flows are cached in the switch, so it's a lot faster. I want to show you a little bit about what you can do just with our simple network again. I'll bring up a couple of terminals. These are X terminals. We'll see if I can move them down and make them a little bigger so you can see them. Let's see, make this, oops, 20. Let's see if those can be seen. Can you see this? Yeah, it looks like it. Okay, on H1 we can ifconfig. So we're going to do something interesting here. We're going to start up a web server. And we're going to actually, we're going to do a couple things. Run Wireshark on our data plane. And look at our data plane interface. Looks good. And we can also run it on our control plane. And maybe connect our, look at our loopback interface. And in particular, we'll look at OpenFlow traffic. And so, and then going back to our host, or actually going back to our other host, we're going to run Firefox. So let's see if you can see that. Looks good. And we're going to go to http://10.0.0.1. If all this works, we'll get some, so we were able to talk to our web server. And the interesting thing is if we look at our data plane traffic, we can see the TCP and HTTP packets. And if we look at our control plane, we can see all the OpenFlow packets. So here's your sort of typical SDN developer scenario where you're looking at both your control plane and your data plane. You have this virtual network on your laptop. And to go a little bit more into the scalability and also look a little bit about what Open vSwitch can do, I'll set up a string of a sort of linear topology where I have a string of 64 switches connected to each other. And so this is a great thing. We're gonna send traffic through the whole string of switches. So actually, and just to make it worse, well, first we'll try pinging it, see if that works. Hopefully this works. Yeah, there we go. See, it's a little slower for this first one, but we're actually going to run iperf to see what kind of performance we can get through. I know Ben's looking unhappy as I'm doing this. Actually, this will probably be surprisingly good. 10 gigabits a second, pretty cool, right? And so that's great, 10 gigabit network through 64 switches. But of course, you guys have heard about megaflows and flow compaction and things. So we can actually do a little bit better if we use OVS patch port. So I have this link OVS type. So this will actually start up a little bit, and hopefully it will give us slightly better performance from iperf because all the flows should be compacted to what's essentially a single flow going through the OVS kernel module. And yeah, as expected, we get like 40 gigabits, which is great on your laptop. Actually, it's in a virtual machine on my Mac, so kind of nice. And unfortunately, it takes a while to stop the links and the switches, but still reasonably fast. And so something you can imagine doing all day, every day, like we do when we develop SDN operating systems and applications. And so just to talk a little bit about how Mininet's built, it's built on, obviously, those Linux features and has a Python API that's really the core of Mininet. And I really believe strongly that dynamic compilation or dynamic configuration using something like Python that has loops is a lot better than just having a huge static JSON or XML or some kind of configuration file. But if you want to do that, you can just load it into Python. It works great. And so here's what the Mininet API looks like. Just simple Python API. You can create a network, add some hosts, add some switches, add controllers and links, send some commands, maybe run the Mininet CLI, shut things down, and that creates this simple network. So you see it's a lot easier to do than entering all the Linux commands in manually. And of course, you can reuse it and have objects and all those good things. And we also have performance modeling in Mininet using TC for link bandwidth limiting and Linux CPU control groups for CPU limiting. So you can actually use a system like Mininet to do performance type experiments. You might think that wouldn't work at all, but it surprisingly does. And if you want to see some examples of this, we used it in a class at Stanford, CS244, the graduate computer networking class. And on our blog, reproducingnetworkresearch.wordpress.com, you can see a lot of examples of trying to reproduce networking experiments and make computer networking a little bit less of cold fusion and try to reproduce something that most of the time you just see in a PDF, but turn it into something you can run on your laptop and try to reproduce. And surprisingly, I guess the punchline is a lot of them, the results are pretty good, and it isn't in fact cold fusion. The things are reproducible. And you can actually use Open vSwitch for performance experiments, which is really neat. So talk a little bit about our experiences with Open vSwitch. I want to just drive it home that network emulation is an incredibly useful application of Open vSwitch. Having a laptop where you can create this distributed system, this interesting network instantly with parameterized topologies and iterate all these different possibilities through all these different possibilities, it's incredibly useful and something that may not be obvious if you just are like, oh, I'll use if you're used to the traditional uses of OVS, just say connecting VMs. A bunch of VMs together in a VM server. And Mininet and Open vSwitch gives you kind of this instant network on your laptop, and emulators are really kind of Swiss Army knives, so you can use it for development, testing, research, demos, experimentation, teaching, pretty much anything you can think of, because it's just a virtual network. You probably don't want to try to compete with rack space using your laptop, but you could. So the good and the bad and possibly the ugly. And now I'm not really an expert on Mininet. I'm an expert on Mininet, but not on Open vSwitch. So I want to tap your brain power as I tell you what happened when we used Mininet and when we used Mininet when Mininet used OVS. And initially, I was really disappointed with Open vSwitch because it was slower to start up and had poorer performance than the Stanford reference switch, which, as far as I can tell, is the predecessor to Open vSwitch. I think you guys wrote it before you created Open vSwitch. And I really missed the Stanford reference kernel switch. But over time, Open vSwitch got really, really good and much better, and its switching performance improved by a factor of 30, which is fantastic. Inclusion in the Linux kernel was a major coup because it meant for Mininet, I didn't have to ship a VM image with a custom kernel, which was a real pain. And I could just have apt-get install it on Ubuntu and Debian. That was really great. Unfortunately, startup performance is still slow due to OVSDB because, as far as I can tell, whenever you run an OVSDB command, it loads in all of OVSDB and writes it back. And so I batch all the commands to put 2 megabytes of commands to try to make thousands of ports at a time, but it's still kind of slow. And OVS patch links are nice. They provide better performance in startup. But obviously, it's a trade-off. You can't TCP dump all the individual interfaces because it's not going through them anymore. And as I mentioned, batching OVSDB commands sort of helped, but not entirely. And there's currently this thing where I want to use TC in Mininet and OVS wants to use TC. And if there are multiple subsystems in Linux that both want to use TC, they can have sort of conflicts over the queuing disciplines. And so I guess it's something to think about. I can probably fix it in Mininet. We sort of have patches for that. But peacefully coexisting with multiple things that want to use TC is kind of a pain. And so I want to suggest or ask you guys about how OVS could possibly evolve to improve support for network emulation. And one thing I really want it to be able to do is to scale to thousands of virtual switches and many thousands of ports on a single Linux kernel. Currently, if I want to do this, I sort of max out because of things like flow table size and things like OVSDB and startup performance and just things in general. It doesn't seem to work well when I get many, many thousands of ports. And I just want to say that that's a real use case that can be very beneficial if you can get it to work. Also, long changes of patch links. I showed you 64 patch links, but I can't get it to work with 65, for example. I'd like to be able to configure the flow tables, for example, change their size and specify the match action support in different flow tables. And something like P4 would help, but it's actually overkill for what Mininet needs, at least. And I'd of course always love to see better performance. 40 gigabits is really great on my laptop, makes me happy. But Volley and NetMap report 70 gigabits on closer to the memory bandwidth on a Pentium 3. So I think performance can still be pushed. Also, I'd like OpenFlow and Linux both to report sort of the correct port configuration and speed of Open vSwitch ports, which they don't currently, and that's something that confuses Mininet users. And in general, I found that I'd like to commend everyone who worked on Open vSwitch for tracking OpenFlow, because that's really what's enabled the SDN revolution and really facilitated things with Mininet. So having OVS continue to track OpenFlow is really, really important. And possibly in the future, tracking P4 and having P4 support in OVS would be fantastic. And so my question for you all, which I guess I'll leave you with, is maybe I'm just out of touch. Maybe OVS can do this today, and if not, how can we get there? So with that, I'll open it up for questions.
All right, we finished a little bit early, so we have plenty of time for questions. So if you have a question, just step up to one of the mics and start talking. Yeah, Bob. If you want to address any of those if you want to talk about any of those in particular, then I mean, what's your top request, I guess?
Oh, I guess it's a good question. I don't know. I guess my top request is maybe scaling, maybe sort of flow table configuration and scaling, sort of the top two on the list. I
Okay.
guess.
Well, let's talk about flow table configuration. Like, what do you mean?
So I'd like to be able to set the size of the flow table for a virtual switch,
Oh,
and I'd also
so-
like to say what matches it supports. Like
Okay.
this is a MAC table, I can match on Macs, this is an IP table, and I'd also like to maybe support say what subset of actions. And so this would enable me to use Open vSwitch to model the pipelines of physical hardware switches, which would be a really super useful thing, and also would perhaps result in more efficient memory usage.
Okay. The ability to limit the size of a flow table is there already, and I can point you to it. The other things of, say, limiting the matches and limiting the actions on a flow table, well, it's not there, and I guess what we'd have to figure out is what's the I don't know, what's the benefit? I guess for simulation that might be good enough, but there's also a couple of ways you can approach that. If you go the ONF route, then you can start supporting TTPs. You can start supporting
Exactly.
the flow table feature request. I think that's the
Right, precisely.
name of it. And either of those would be. I mean, there's no reason they can't be implemented. But of course, they'd be some work, and we'd just have to figure out who is the best person to do it.
Yeah, you mentioned limiting flow table size. How about expanding flow table size? Say, if I say I would like to allocate, 100 switches that each have like 100 or 1,000,000 flow table entries.
Well, I think you'd have a trouble fitting 100 times 1,000,000 flows in a machine, but.
Well, that's the other thing, I guess. If they were narrower tables, then for example, you might be able to fit more of them.
Oh well, the cost of a flow table entry is it's not proportional to the potential size of a flow. It's proportional to the fields that it actually matches on. If you only match on the IP address, then it's going to have less cost than if you match in every field.
So 1,000,000 IP addresses, that's what, 4 megabytes, right? So I could easily have 100 of those. That's 400 megabytes, right? So that's the kind of use. That's something that'd be. It's not perhaps useful to most users of OVS, but it's really useful for people who want to do simulation or emulation.
So I think you just proved that it can't fit in memory. So I guess I don't
What's wrong
understand
with
the request.
400 megabytes? I have 400 megabytes in memory.
400 megabytes, but you realize there's more overhead than just the IP addresses, right? Or maybe that is your request, that the overhead should be exceedingly low?
Well, both actually. Yeah. I mean, I guess the point is that in other software switches, I can make bigger flow tables than I can in OVS.
How you mean that? Say there are switches where they would use less than 400 megabytes, or they use exactly 400 megabytes?
Well, they'd use close to 400 megabytes. I mean, I can write.
Okay.
I wrote a switch in an OpenFlow implementation in Python, which just basically, I mean, it's not efficient, but it uses a small amount of memory, and so that's something. I guess it's something.
Okay. Well, it's
so.
If that's something that a lot of users want, then we should figure out a way to do it. Or if important users want it, and Mininet is, if it has a lot of users, then arguably it's important. So we should figure out a way to do that.
That'd be great. Any other questions?
So I had a very basic question. I know in the conference there will be more discussions on containers. How would containers be simulated in your environment if there is a plan, if a vSwitch sort of is needed? So that answer would be good. And the previous talk, Duarte talked about a database. He showed gateways, VMs, and the gateway for the router, the database for the routers. And he said there is no controller. Can he please explain, and this is also a very basic question, what does it mean not to have a controller but having a database?
Well, I can't answer necessarily for the previous talk, but my assumption is that with the database, you put your state in the database, and the distributed implementation just queries the database and updates it. And so that way you can sort of have a symmetric kind of peer-to-peer sort of implementation where there isn't centralized control per se, but there's a centralized data store which is used for synchronization and for consistency. And regarding containers, Mininet's precisely a container orchestration system. So, you know, there are other container orchestration systems which are good, things like the Docker or LXC, but those usually have more, and from my perspective, they have more complexity and give you more than what I actually want for just simple network simulation. I don't want to worry about I don't want to worry about base disk images. I don't want to worry about, you know, actually booting up an operating system. I don't want to worry about other things that I don't really need. Just having a process attached to a virtual Ethernet interface is really good for 90% of the cases. However, there's no reason why you can't attach other containers to Mininet. I mean, somebody made a Docker host object for Mininet where you can instantiate Docker instances. It's possible to attach physical ports to Mininet and plug it into your real network. You know, one of my favorite applications is running Mininet on a Raspberry Pi. I call it Network in a Box, and you plug in a bunch of like USB Ethernet ports to it, and so you have this virtual network that you can plug into your physical Ethernet. There are lots of things you can do, and so I think containers are sort of the future for lots of things, but I want to suggest to all of you that perhaps, you know, the simplest containers are maybe what you should be thinking about for a lot of things, and you don't need the whole complexity of a full operating system, and certainly not a full VM to run things like NFV.
All right. If there are any other questions, we still have another minute. Otherwise, let's thank our speaker.